This is the ROS Developers Podcast, episode 46.
The ROS Developers Podcast, the ROS Developers. The ROS Developers Podcast, the ROS Developers.
Hello, ROS developers, and welcome to the ROS Developers Podcast, the podcast that gives you insights from the experts about how to program your robots with ROS. This is Ricardo Tellez speaking from the Construct, and today I would like to dedicate the podcast to the people who is already thinking about the summer holidays, going to the beach, having sun, drinking something cold, and your robot playing in the water. That's it. That's the best dream of the roboticist. Yes, I know that you know somebody that thinks like that. Yeah, like for example myself. Yeah. So anyway, today it is my pleasure to introduce you Nils Bore. Nils is a postdoc at the Division of Robotics, Perception and Learning at the Royal Institute of Technology in Stockholm. There, he is developing underwater autonomous vehicles within the SMaRC project. And Nils is here today to tell us more about how to develop ROS-based underwater autonomous vehicles. Welcome to the podcast, Nils.
Thank you, Ricardo, and thank you for having me. I'm honored to be on the show.
Okay, did I mention properly? I think that I did it the other way around. It's autonomous underwater vehicles?
Yeah, exactly, AUVs.
Okay.
I think it's as to not confuse it with UAVs, basically,
okay.
Which are a bit more well known.
Okay, because the UAVs are unmanned autonomous vehicles. Okay, yeah, that's correct. Okay, so I don't know. I think that I mentioned wrongly in the introduction some way, but anyway, we understand.
Doesn't matter.
Yeah, and then I was telling to the listeners that you are working for the SMaRC project. What is the SMaRC project?
It stands for, it's an acronym, so it stands for the Swedish Maritime Robotics Center. It's basically a consortium of Swedish companies, universities, and other institutes that are interested in underwater technology and primarily AUVs.
Okay.
I'm just going to say AUVs, and I hope the listeners have grasped that it's these autonomous underwater vehicles. It's a long thing to say every time otherwise.
Yeah.
But basically, the main purpose of this consortium is kind of developing the technology for the next generation of these AUVs. So I think it could be a good thing to kind of start just shortly explaining the concept of an AUV, because there are slightly different variations there where you talk about autonomy and, in the maritime domain in general.
Okay.
So you have autonomous surface vehicles or unmanned surface vehicles.
Okay.
Which are basically like autonomous boats, similar to how you have autonomous cars on land.
Okay.
And then you have kind of the underwater stuff, which is you have ROVs,
okay,
which are remotely operated vehicles. So that's currently the most common thing in, when you do underwater inspections or something, that you have a tether going down to an underwater vehicle and then you control it. Some operator is sitting at the station controlling it.
Yeah, because you don't want to lose it. Yeah.
Exactly. And then you have this also unmanned underwater vehicle, and it's kind of a floating concept there. What should be considered an autonomous underwater vehicle and what's an unmanned underwater vehicle. But that's more in the direction that we are working, that it should be a completely autonomous vehicle operating with no connection to the surface, or only sporadic connection to the surface.
Okay.
But
the unmanned underwater vehicle would be what we are calling the autonomous underwater vehicle. Is the same concept, or does it have a difference?
I would say it's kind of a broader concept. I should also say I'm kind of new to the field, so I hope I don't tread on anyone's toes here. But
don't worry.
It's kind of with the autonomous vehicles is within the scope of unmanned vehicles.
Okay.
But what I was getting to is that currently most of these kinds of vehicles, even though they're not tethered, they mostly have some kind of connection to the surface through an acoustic link or something. And it's the duration of the autonomy is somewhat limited. So kind of the many of the goals that we have within the consortium is extending the duration of autonomy for these vehicles and making sure that they can do more complex tasks for longer amounts of time. Yeah,
longer. And then what is your specific role there at this consortium?
So basically we're doing research in different areas. So I would say my role is mostly towards this autonomy and perception. So I mostly do, in my research, I do work on underwater perception and underwater localization and SLAM.
Okay.
And then there are other people within the project also doing research on communication, like building hardware for acoustic underwater communication, and also for building the hardware, building the vehicles, the actual AUVs that we are then building the software for.
Okay. So in your case, is more related to the software. So that's we are in the right place, okay? Because this is the ROS Developers podcast. Very good. And then do you have Do you have experience working with wheel robots before?
Yeah. So again, that's up until like 2 years ago. I was working with indoor service robots, part of this large European Strands project. So I have quite a bit of experience there, really much more than I have of underwater vehicles.
Okay.
Yeah.
And which are the challenges that a roboticist faces when you are working with water vehicles instead of the wheel robot? So what is the difference?
Yeah, so it's, I would say mainly, well, of course, it's a whole big, like, different thing that you're not seeing your vehicle, right?
Yeah,
and
exactly.
When you're testing, you don't really see what's happening at any given time.
Yes. That has to be scary, isn't it?
Yeah, it's scary. The thing is, we're still kind of limited to pool tests so far. So we haven't really let it down into the depths yet.
Okay.
But it's gonna be scary. That's for sure.
But then your tests that you have done up to now are in a swimming pool or something that is very controlled place?
Yeah, you could say that. So we're still in the development phase of the vehicle. We're not doing any real deployments like for data gathering and stuff. It's still developing the hardware and the software.
Okay.
So we're building actually multiple vehicles, but I'm mostly involved in one of them, and that's the one that's going to be totally ROS-based.
Okay.
But then the other interesting aspect is, this thing that you don't see the robot as you're doing the testing means that you need to be much more careful in like what kind of ambition you have with each new thing that you're doing, right?
Yes.
So you have to be very conservative the whole time with all the new things that you deploy on the robot. But the other aspect is also that you tackle different problems in terms of both in planning and control and in localization and mapping.
Okay.
So if you start with planning and control, of course, if you compare with like a service robot that I worked on, or with an autonomous car, you don't need to be as careful, like not to run into people and stuff. There are not so many people swimming around in the areas that we're testing that we can run over or anything. So again, the scarier part is losing the robot.
Yeah, because it goes somewhere and never come back, and nobody sees it again.
Exactly. So that's basically what happened to the precursor to the robot that we're currently building. Yeah. So
wow, that has to be very sad, because you spend a lot of time, a lot of money there, and then you lost it forever.
Yeah, fortunately I wasn't involved in that project, but it makes you humble now that we're building the precursor,
you are the next, so better watch your steps.
Yeah, exactly.
Okay.
So I would say that there you're more worried about keeping the robot safe rather than keeping surrounding humans, and you don't really have that many vessels either, because you're trying to run underwater as much as possible, where you don't have boats running around.
Okay.
And then if you go to localization and mapping, it's also kind of a different problem, though in large parts it's similar. We have different sensors. I guess we'll get to that later.
Well, you can tell us which type of sensors are you using?
Maybe that's actually relevant to talk a little bit about that before, because that's ties into that question. Well, first off, you have kind of the normal stuff. You have, like an Imu, gyro, something you don't have on indoor robots, but probably on cars, is a compass.
A compass.
That we have as well. So that helps us a lot, knowing the direction when we're doing dead reckoning. And then you have some more specific sensors. Actually, one thing that's kind of interesting is that you're hugely helped by having an accurate Imu and gyro, because that's one of your main sources for your dead reckoning. So usually you would probably, on the high-end AUVs at least, you would find very expensive, good, especially gyroscopes. So you have kind of these ring laser gyros, but we're mostly working with a lot cheaper stuff that's more similar to what you find in your average robot or something.
In the wheel robot.
Yeah.
But then
you have...
Yeah, sure. Go ahead. Yeah,
then you have some more kind of specific sensors. If we stay with the dead reckoning stuff, or what you need for dead reckoning, then you also have the altimeter, which is a kind of sonar, a single beam sonar you call it, that just sends out a single pulse and measures the time it takes it to go to the seafloor and back to the vehicle.
Okay.
You also usually have a pressure sensor, and that tells you how deep you are with respect to the surface of the ocean.
Okay. And what do you use this for? In order to understand the depth at which the robot is?
Exactly. So that's basically that tells us the depth to a pretty high degree of accuracy.
No? Okay.
So that limits you, at least it limits the position to a two-dimensional problem.
And do you have any sensor for detecting obstacles, like a sonar or?
Yeah, I'll get back to that later, because we have we definitely do, but we also have one more sensor that's very common for doing the reckoning.
Okay.
And that's this thing called the Doppler velocity log.
Okay, what is that?
It's basically, it's usually you have 4 sonar heads underneath the vehicle, and then you send out again a sonar pulse, usually towards the seafloor, and it measures the Doppler shift of the pulse
I see.
with respect to the outgoing wavefront, basically.
Okay.
And by having 3 or 4 of them, you can get basically a 3-dimensional velocity vector.
Speed. Okay. Very
Yeah,
very
so
clever. Very clever.
Yeah, that's. I think. I mean, it's not always been used in AUVs. Like initially, when AUVs were developed, I think they didn't have them, but then this was kind of a huge. When they started to use them, it made a huge difference in the precision of the dead reckoning.
And one question, wait a second, because you are mentioning dead reckoning a lot, and then can you explain to the listeners what do you mean by dead reckoning?
Of course, yeah. So it's basically integrating your position from acceleration, both I guess linear and angular, and velocities to kind of estimate a global pulse of your vehicle.
Exactly. So in terms of wheel robots, we could say that is kind of computing the odometry of the robot.
Exactly. Summing up all the spins of your wheels on the robot, for example.
But then you have some, you should have some error in this measurement that you should correct at some point in time. And how do you do that?
Exactly. So the error, I think it grows something like quadratically with time or something.
Wow.
And of course, then as you go along, it will just grow. So if you want to operate the vehicle for extended amounts of time, you need to correct your estimate somehow. So one way of doing it, of course, is just to surface and get a GPS fix. That's the easiest way of correcting your dead reckoning drift.
Okay.
And then you can also kind of go back and do kind of a smoothing operation to back correct all the previous positions that you visited before. The other way of doing it, the one that I'm working more towards, is doing SLAM to correct the reckoning drift. And then what you would do is you want to find a loop closure constraint to some previously visited place that you can recognize with some sensor when you come back to that place and know that you were there before, and then you can kind of correct all of the drift that happened since you last visited that place.
Okay. And for that you need a laser, or what do you use? A sonar?
Yeah, so that's a problem with basically all kind of electromagnetic sensors, including GPS, radio, lasers, is that they all get absorbed in the water volume, basically.
Yes.
So I probably should have started with that, but that's why we can't use GPS, for example, underwater. You can use cameras to an extent if you have clear visibility in the water, of course, and you don't want to look too far.
Okay.
Uh, so some people in the underwater community are doing that, and then you're doing visual SLAM. Usually aim a camera at the seafloor and track how the features are moving from frame to frame. But we are focusing more on sonars, and I think that's kind of the way you have to go if you want to look at a larger area of the seafloor, and probably if you want to be more robust to the ocean conditions, the visibility and so on.
Yeah, that has to be very, very tough. That because doing localization with sonars is very difficult, and also is not very accurate.
Yeah, I would say that the sonars that we use on land on robots are a bit different than the ones we have underwater.
Okay.
So you can on many AUVs you can carry much more capable sonars that have been developed for doing actual service from big ships and stuff.
Mm-hmm.
For that kind of thing, you have this thing called a multi-beam, which is basically you send out a bunch of different beams in different directions, and then you get kind of like a laser scan. You get the distance to the seafloor in this kind of planar cross section that you're measuring at the moment, and the precision there can be fairly good. So it's not so different from having a laser scan in some sense.
Okay, I'm impressed then about that. I had no idea that existed. That's super cool. And then why we are not using this in the robots, in the wheel robots?
Well, one thing could be that they are fairly big, but I think that there is some basic differences in how you construct, underwater sonars as opposed to ones that are based in air.
Okay. So they are taking they are taking the properties of the water into account, and in order to design that will not work in the air.
No, they can be the sonar elements can be damaged if you fire them up in air, basically.
In the air,
so they won't give you any meaningful measurements.
Okay, I see.
But I'm not again a expert on the sonar hardware, so I'm more on analyzing the outputs.
Okay, great. And then another thing is about the actuators. So how do you make the robots move?
I actually want to kind of just finish the
sure. Go ahead.
The thing about so the interesting thing about doing SLAM with something like this multi-beam is that, I mean, as I said, you have kind of this planar view of the seafloor, right?
Yeah.
So it's kind of like you have this planar laser. I think you usually call it like a push broom laser. Okay. So you kind of you just see a section of the surface at a time as you're going along, and it's pointed downwards.
Yeah.
So basically, as you're going, you're seeing new terrain the whole time.
I see.
You're not seeing anything that you just previously seen. So that means you can't do any tracking as you're moving.
Okay.
So like if you do like visual SLAM, you usually have several components. One of them is the tracking of the visual features as you're moving to kind of correct the short term drift in your position estimate. But we don't really have that opportunity to do the tracking. So we only basically we have to short term just estimate the position with these inertial sensors and the DVL, and then for the loop closures, then we can use the multi-beam, for example, to be able to recognize a previously visited place.
Okay,
So
when you go back.
that's a slight, yeah, exactly. So that's a slight difference to some robotics applications.
Yes,
It's
it's
the
actually.
same if you have a laser scan.
Yeah, because you are working on SLAM directly. So it's like when we have a weird robot that it's in an unknown location, then it is moving around and then it's building the map. So basically your robot is most of the time is doing SLAM all the time, I would say. Could it be a good meta?
It's basically, you could say that initially we're basically just doing dead reckoning and mapping in the sense that, just accumulating the measurements based on the current estimates. And then when we get a loop closure, we can start correcting with help of the sensor measurement.
Okay, and then you can correct the error backwards also in everything.
Yeah,
that
exactly.
You have. Okay. I think that I got the idea of the technique. And then about the actuators, then how do you move the robot?
So it's a bit different between different robots. Generally you have some kind of thrusters or propellers. So to make it move forward. Sometimes you also have some, if we talk generally, you sometimes have AUVs that look more like UAVs or something, in the sense that, they can move in multiple different directions. They have many thrusters, so they can move back and forth and to the sides and stuff. We are more working with something like torpedo-shaped AUVs or similar stuff. So, like cylinders, which are generally moving forwards. And then you have rudders to be able to steer. In our case, we actually have vectored thrust on the thrusters. So we can rotate the whole thrusters to be able to steer the vehicle. And then you also have, depending on your AUV, you typically have what's called a variable buoyancy system. So basically you can, pump more or less air or water into the vehicle to make it more or less buoyant.
Okay.
And that's, in that way you can,
control.
Make you don't have to put as much load on the thrusters and the control surfaces. You can, make it neutrally buoyant at the depth that you want to be at. So that it just sits at the proper depth, and you don't have to work against any buoyancy or anything. You can just go forward.
Okay.
And then sometimes we definitely do, and that's one of the interesting aspects of the vehicle we're building, is that we have several trim systems to kind of move this center of gravity in the vehicle around.
Okay.
So we can, put it more to the side or further forward or back to, make the nose go up a little bit or down a little bit and so on. And that makes the vehicle a bit more agile in the kind of controls or kind of things it can do.
Like the height or the depth at which it is. So it allows you to move faster into a higher position or a lower position. Yeah. Okay.
And then with this trim system, you can also make the vehicle, rotate a little bit. So you have your sensors pointed a little bit to the side, maybe. If you roll it a little bit to one side, you can see a little bit to one side. And if you roll it to the other side, you can see that side. But this is kind of more specific to our vehicle. And I would say not something that you see on every
Oh,
AUV.
okay. So is the let's say is the stamp of your institute is the mark that you are doing?
Yeah,
in
exactly.
the
It's
field.
one of these things that we're investigating for the next generation of AUVs. So
Great.
if for this thing, we're kind of, we wanted to be able to operate, for example, in a blue farming scenario where you have, you have these algae farms in the ocean that you want to monitor continuously to see that there is no fouling or anything, and that the algae are not growing enough. And then it's interesting to be able to rotate the sensors while you're going through these narrow passages to kind of look around and inspect all of the different parts.
Oh, amazing. And then I think that now it's time to start talking about Ross. I mean, we have been talking for half an hour, but Ross is not here yet. People is getting nervous. No, it's okay. I mean, I'm just making the hype now, to people. Oh, now
sure.
they are going to talk about Ross. And so what is the role of Ross in the whole architecture?
Yeah. So I should probably have mentioned that I'm trying to be this kind of software architect on this project. So that's one of my roles in this project. But mainly it's just used as a middleware to be able to communicate between different parts of our autonomy stack, right? So basically the typical use case for ROS. I would say that the case for ROS is maybe not as strong for an AUV as for a typical wheeled robot, because there are less components available for using on an AUV. I mean, there are some. For example, the dead reckoning that we're using now is based on the robot localization package.
Of ROS, you mean? Of the
exactly.
of the navigation stack.
Yeah.
Great.
Basically, the robot localization package. But I would say some of the main highlights, and I mean the main kind of the place where ROS really shines is the community and all of the resources that you have online and all of the experience that our PhDs and master students already have with ROS. And they enjoy working with ROS. So I would say that that's really the main selling point for us. That we already have, competent people that can get in there and start doing stuff.
Exactly.
Just by knowing ROS, they can start and figure out what we're doing here on our AUVs. So that's very important.
Exactly.
Then of course you have stuff like TF and RVIS, which are very convenient.
Yes,
so
super
that's
cool
another
tools.
big thing.
Yes.
Yeah.
But you mentioned when I sent you the request for doing this interview, you mentioned me that you were using ROS in your project, but you also needed to connect with other frameworks. Which are, and you mentioned specifically that those frameworks are more mature in the underwater vehicles scenario. So can you explain us which frameworks are those?
So I would say primarily what's kind of been missing for us is a way of planning our missions. So typically when you plan these missions for AUV, you want to have some kind of visual tool where you see you have your sea charts, you can see where all the how deep it is, where all the islands are, where all the shipping lanes go, and so on. And then you typically there are different things that you want to do. For example, plan a survey pattern to cover an area of the seafloor and so on.
Okay.
And for that, you have several tools available that's been used for a long while in the AUV community.
Okay.
So one such tool that we've decided on using is called Neptus, and they have this IMC middleware, so similar to ROS that they're using. So that's one thing that where we've had to bridge ROS with another middleware to get this mission planning capability.
Mm-hmm. One question. When you say mission planning, what do you mean?
Yeah.
For us, it is to visit some areas or to create a map of the area, or what is exactly mission planning?
Yeah, so it could be just, give the robot a list of waypoints to go to.
But so waypoints based on what? On what information?
In that case, it could just be, lat long coordinates and a depth, for example.
Okay.
So basically 3D positions in the world, on the globe.
Okay.
So similar to, the waypoints that you would give move base in the classical navigation stack.
Oh, okay, but then you have already a knowledge. Well, the robot knows already the area.
Yeah, typically that's the scenario. It depends a little bit, but typically you have some access to, some rough sea charts or something.
I see.
You know approximately how deep it is.
Okay.
But in some scenarios you might not. But yeah, maybe that's for another podcast.
Okay.
And then it could be also that, as I said, you have an area that you want to cover with your sensors, and then you can typically in your mission planner you kind of specify which area, and the planner can help you make up a trajectory that you need to follow in order to cover that area.
I see.
It's stuff like that.
Okay, yeah, that would be. So it's what is lacking ROS in this subject, in the subject of underwater vehicles is not the connection to the actuators or sensors. Is more higher level tools for planning, basically.
Yeah. Another thing, while we're on the subject, and we had this kind of meeting about underwater ROS, which it took place outside Boston last autumn, actually.
Mm-hmm.
So they called a meeting for basically the underwater ROS community to come together and discuss what was currently missing in ROS and what we could do to advance the state together as a group.
Mm-hmm.
And I would say one of the other main things that was found to be missing at that meeting was underwater simulations also. So basically, better support in gazebo for underwater, mainly, vehicle dynamics and stuff. So that's another thing. But I mean, it's still, you can use surprisingly large amounts in ROS for this domain as well. So that's promising.
Yes, okay. And then you mentioned several things now. Then let me go one by one. First one, you mentioned about this underwater ROS community. Is there any place, or if the listeners, they are interested on this, is there any place that they can join this community in a specific webpage or channel?
I would primarily point listeners to the underwater, I think it's called the Underwater Robotics Discourse. So it's on the normal ROS discourse. There is a topic that I think is called underwater, maybe underwater robotics.
Okay.
Okay.
I will check.
Yeah.
I will check that and then put a link beneath the podcast description, so anybody can check the link there.
Perfect. But that's kind of something that's very active now, or something that's in progress, that we are trying to formulate what kind of message definitions we should have and so on, so that we can kind of interoperate easier and things like that. So that's kind of the steps that are needed to get to the level of the larger robotics community that already have a lot of these common tools that they can work on.
Okay. Do you know that there are, so what you are doing already is also in progress, being done by the ROS Agriculture Group. So they are working also with agricultural robots, and they are trying to also to see what ROS is missing. They are creating a lot of stuff. So I think that your community underwater ROS, then I think it's going to be, maybe you can learn one to each other, maybe, I don't know.
Yeah, I think Tallyfoot, who you interviewed in one of your previous episodes, was there during the meeting, actually, and I think he mentioned something about this agriculture robotics.
Yeah, well, we interviewed a guy from the actual ROS Agriculture Group that is called Kyler Laird, and he's doing amazing things with with tractors, super big tractors, and then they put those tractors autonomous. They put autonomy there, and it's based on ROS with using different electronics and computers. And that's amazing to see them move by themselves on the fields.
Yeah, it sounds super cool.
Yes.
Very useful, probably.
Yeah. Well, I just wanted to point, in case that is useful for your community, to take some ideas from what they have already done, because it's also a very young community. So.
Yeah, and I would say, the structure of all of this is one of the main problems, probably. How you organize the community and how you agree as a community. That's, I think, one of the main things that we'll have to figure out, definitely.
Okay, so then listeners, if you are there, you are working with underwater vehicles, or you would like to, then here is a community. You can contact the Nils also. I will put his details also beneath the podcast, and join the community and help them grow, of course. And let me go after this commercial for the Underwater Robotics Group. Let me ask you more questions about ROS. So then, how do you test your robot? So do you go to the pool? You were telling me something, but can you tell us the actual procedure that you are going to follow? Because still you don't have the robot, but what are you going to follow?
Yeah, we do have the robot.
Oh, okay.
But right now, one of the things that we're missing is a thruster. So we're mostly testing out our buoyancy system that I talked about previously.
Yeah.
And the trim system. So what we're doing in the pool is we go there. We have currently, because we're at this stage, we have a cable running into the robot. So we can see everything that's happening in the ROS system as we're testing. And we can see if it's leaking, for example. It's because we have these leak sensors in there, which is very handy. And then we try to control the vehicle to stay at different depths, for it to have different attitudes, So, roll it and pitch it backwards and stuff. And then we're, running a kind of a mission plan with this limited vehicle that we're can go up to a certain depth, go to this roll angle, going down, and then finishing the mission going to the surface
again.
But then I think in 1 or 2 weeks we're also testing the thrusters. But then again we'll have it tethered on the first try, so we can actually see what's going on inside the vehicle and so on. But that's going to be very exciting.
Oh yes. Would it be possible? Do you have any YouTube channel that we can see anything of your results?
Yes, we have.
I think that could be interesting.
Things. At least we have for our other vehicles. Like I'll check about the one I'm talking about now. I'll send you a mail.
Okay, please. So I will include here in the documentation of the podcast. Because that has to be exactly. You say it has to be exciting, yes, to watch it really. And,
it's very exciting, and sometimes it leaks, and then you have to bring it up as quick as you can, and try to figure out why it's leaking and so on. So it's very exciting.
But then what about the use of simulations for testing? Are you using simulations? You mentioned before, but how much use are you doing of the simulations?
Quite a bit. So again, we need to be very careful as to what kind of software we're deploying on the real robots, so that we don't lose it, or something crashes and it brings the whole vehicle to the seafloor.
Yes,
I would say we do much more testing in simulation than we do in the pool currently, at least.
Wow.
But that's mainly as a way of testing the full system, doing a mission plan, doing everything it's supposed to do, and seeing that all of the components work well together. So it's kind of a high-level simulation that you can mostly use to try out the larger software system and how all the different software components interact.
Okay. And do you see much difference between the simulation and the actual robot? And for example, when we use wheel robots, so we can see the differences. But depending on what we are testing, then the simulation is quite useful and is quite close to reality. For example, when we are doing a map of an area, that is very good already. It's very close, the simulation, to the real world. Also, some things for detecting objects by perception, for example, is also quite nice, the gazebo simulation. But for other things like grasping, then the simulation is very bad. It's very far from reality. In your case?
I would say it's probably closer to grasping. So one thing is that, there are a lot more unknowns in the underwater domain, because you have, like currents, you have more things that you're not in control of. So a current will make your robots, just drift away a few meters if you run into it, or stuff like that. And then again, gazebo is, as it is right now, not really optimized for simulating the dynamics of an underwater robot. So that's another, point that makes it, specifically in our case, a bit less realistic. But it's still very useful to try out, the higher level system. The other thing is that the sensors are quite hard to simulate, actually.
Yes.
So typically you need more than just the geometry of the environment to be able to simulate these sensors. You need something that in some way characterizes the acoustic properties of both the surrounding ocean and the seafloor that you're observing. So that's a little bit different.
Yes, I can imagine. I don't know how you can do this, how you can simulate that. I think it's going to be complex. About the dynamics, there are some buoyancy plugins that you can use and that they work more or less. I suppose that you're already using them, the buoyancy plugins.
Yeah, we're using something called a UUV simulator. That's a kind of a gazebo extension that's actually very nice. That handles a lot of the things that you need for an underwater vehicle. So that's something that's been very useful.
Okay.
But I'm also not sure if you actually need that detailed of a simulation. The thought process that we currently have is that you can test more, like system level stuff in Gazebo, where you can simulate the whole thing, with the vehicle, the sensors, going from waypoints, so on. Yeah. And then you can simulate more dynamics in another simulator, maybe.
Yes, that's a good approach. Yeah, because it just depends on which level are you testing. Your programs,
exactly.
Your control programs. Then you don't need to have so much detail in the physics, because it's about. The control, the mission programs, the mission control programs. But if you need to test about the specific test of the propeller's control in order to get up or down or forward or backwards or turning, then in that case you will need more physics accuracy.
Yeah.
Okay.
And I think it's the same thing if you look at service robots, for example. There are lots of things there that are very hard to simulate. If you think about people moving around or moving objects around and so on. Your map changing, then it's also at some point it's going to be hard to simulate, and you're more testing for slightly different things, but it's still very useful.
Okay. And then I see that you have the simulations on your Git, so I will put a link also on the podcast description for people who can download in this UUV simulator also, and they can test it. That is quite close to the upgrade to Gazebo for underwater vehicles. And then let me tell you one thing. So why did I contact you for the interview? Actually, it was for another reason. It was because I saw a post of you at the ROS discourse talking about a series of packages that you have released that are called Flex ROS.
Right.
So what is Flex ROS? Are you using this Flex ROS for your underwater vehicles?
Yeah, so basically what that came out of is actually that we needed some interface for these pool tests that I was talking about. So the guys that are building the UVs, they don't want to be typing ROS topic pub or something to change the position of the actuators. So then I figured I need to make some kind of web interface where you say, go to this step by pulling a slider or typing it into the web page instead. So that's kind of why Flex ROS. And what it is basically a wrapper or a library working with another library called Flex. And what Flex does is it allows you to write web pages entirely in Python. So it has this kind of Python to JavaScript transpiler that allows you to run basically some kind of Python on the front end as well as the back end. And they can communicate in between these two, the front end and the back end, running using WebSockets. And what I did was I added a ROS connection so that you can also run, ROS publishers, services, action clients, so on, through these WebSocket interface. And I thought the results were pretty nice. You can, you can write a very a web page with some controls and publish and subscribe to ROS topics in a very concise packet. Yeah. So that's why I decided I should publish it on ROS Discourse and make some decent documentation.
Yes, exactly. And it's a very good idea, because then it's very easy for us that we are used to program in ROS using Python, for example, then to just use a little bit more and then create a good interface, a web interface for our ROS program. And then from any device that is connected to the robot, then we can control the robot or see what is happening on the robot, even from a mobile phone. It's super convenient.
Yeah, and I've worked a little bit with, I think it's called ROS Bridge, right?
Which one?
Sorry? ROS Bridge.
ROS Bridge, yeah.
So basically a JavaScript client library for ROS. And it's quite nice, but the problem is I don't really know how to program in JavaScript and HTML. So then this is a decent option for me, at least.
Also, yeah.
And I suspect quite a lot of ROS developers might know more Python than
the JavaScript.
HTML and JavaScript. Yeah.
Yes, that's it. Okay, so Nils, we have reached the end of the interview here. I had I had two more questions there, but you have already answered before, so I think that is a good point if we finish here. And
I apologize if I answered the questions at a length that's
no, it's
a couple of points there.
It's okay. Very good. Yes, that's very good. The thing is that sometimes there is a small delay between you and me, and then sometimes I don't know if I have to interrupt or not, and then that's those things that happen, But it's perfect. Very good. Thank you very much for all the information, and I wish you the best of lucks when you release the first time your robot in the sea. In the sea there, that's the tough test. So best of luck.
I'm going to cross my fingers as well. Thank you.
Best of luck. Thanks a lot, Nils.
Thank you for having me on the podcast. It was a pleasure.
Okay, our pleasure here. Thank you. And for all the listeners, let me remind you that in 1 week, we are going to have the second edition of the ROS Developers Conference. The ROS DevCon is a hands-on conference. And what does it mean? It means that you will not have just to attend and listen to the speakers, but also practice at the same time with them. It is an online conference, so you don't have to travel. You only attend the conference through internet. You only need to have a computer with a web browser and connect to the conference and start programming in ROS with the speakers. It's going to be a lot of fun. We are going to learn a lot, and it's going to be an amazing second edition. Check all the details at the web address that I'm going to put down here, but also I'm going to say is rosdevcon.com. Okay, that funny name. And that is all for today. See you next week with a new lesson from the experts. And until then, remember, keep pushing your ROS learning.
podcast, the ROS developers.